All right, welcome. Today we're going to pull back the curtain on a totally invisible property of light, something called polarization. It sounds kind of complicated, I know, but trust me, by the end of this, you're going to understand the physics behind what seems like a cool magic trick.
So you've probably done this yourself, right? You're wearing polarized sunglasses, you look at your phone, and as you tilt your head, poof, the screen goes completely black. What is going on there? Well, it's not magic, it's some really cool physics. And yeah, we're going to solve that exact mystery right now.
Okay, here's our game plan. We'll start with the two faces of light, then look at the job of the first filter. After that, we'll get into the rule of the second filter, and finally, we'll see where polarization pops up in your world. Let's do it!
All right, first up, the two faces of light. To really get that sunglasses trick, we've got to understand how light actually works. And, the light coming from the sun, or even a light bulb, it's a mess. It's totally chaotic. But the cool thing is, we can bring some order to that chaos.
Okay, so light travels as a wave, and that wave wiggles or vibrates up and down, side to side, perpendicular to the direction it's going. Now look at this. The light on the left, unpolarized light, is just vibrating in every direction at once. It's wild. But the light on the right, that's polarized. It's neat, it's orderly. All its vibrations have been wrangled into just one single direction, or plane. The textbook we're looking at has a perfect analogy for this. Think about shaking a rope. If you just shake it like crazy in all different directions, you've got an unpolarized wave. But what if you just shake it straight up and down? Only up and down. That's it. That is a polarized wave. It's that simple.
So that's the official definition of polarization right there. It's just restricting those wiggles to a single plane. And this is actually a super important concept because it's one of the key pieces of proof that light is a transverse wave. You see, you can't do this with a sound wave, which pushes forward and back. Only side-to-side waves can be polarized.
So the big question is, how do we actually do that? How do we take that messy, chaotic light and make it nice and orderly? Well, we use a special tool. Let's talk about the first filter's job.
The best way to think of a polarizer is like a picket fence with really narrow slots. Now, when all that messy, vibrating in every direction light hits the fence, what happens? Well, only the parts of the wave that are vibrating up and down, the ones that are aligned with the slots, can actually squeeze through. Everything else, blocked. And what comes out the other side is that beautiful, clean, vertically polarized light.
Now here is a really important number, 50%. When you pass unpolarized light through that first filter, it always cuts the brightness in half. It gets rid of 50% of the light. Why? Because it's blocking half of all those random vibrations. And that right there is the first clue to our sunglasses mystery. It's why they make everything look darker. Okay, so now we have our nice, orderly, polarized light. But what happens if we put a second filter in the way? This is where things get really interesting. Let's talk about the rule of the second filter.
So check out this setup. Light comes in, goes through that first filter, the polarizer, and comes out neat and tidy. Then it hits the second filter, which we call an analyzer. And here's the absolute key to everything, the angle between those two filters. That angle is going to decide exactly what happens next.
And it all comes down to this one elegant little equation. This is called Malus's law. Now, don't let the symbols freak you out. This is literally the secret code that explains why your sunglasses make your phone screen go dark. Let's break it down.
It's actually pretty straightforward. I is just the final brightness, what you see at the very end. I naught is the brightness of the light after it's gone through the first filter. And that little symbol, theta, well, that's just our all-important angle between the two filters. So basically, the final brightness depends completely on the cosine squared of that angle. That's it.
And this graph shows it perfectly. When the filters are perfectly lined up so the angle is 0, all the light gets through. Maximum brightness. But as you start to rotate that second filter, look what happens. The intensity drops. And when you get to exactly 90 degrees, the cosine of 90 is 0. 0 squared is still 0. Boom! No light. It's completely black. And that's the big reveal. The light coming from your phone screen is already polarized. Your sunglasses are just the second filter.
And what's so cool about this law is how precise it is. Let's say we want to cut the light down to exactly 1/4 of its brightness. Okay, we just plug that into the formula. 1/4 of I naught equals I naught times cos squared theta. The I naughts cancel out, so cos squared theta equals 1/4. We take the square root of both sides, so cosine of theta is 1/2. And if you remember your trig, or just use a calculator, you'll find that the angle has to be exactly 60 degrees. How cool is that? We have total control.
Okay, this is a super important point, and it trips a lot of people up.
If the light coming in is unpolarized, that chaotic, messy stuff, then rotating that first filter does absolutely nothing to the brightness. It doesn't matter what angle it's at, it's still just going to block half the light. The angle only starts to matter for the second filter because it's working with light that's already been organized into a single plane.
So this whole thing isn't just a neat trick for physics class. This property of light is used all over the place, in technologies you probably use every single day. Let's look at polarization out in the real world. I mean, we've already talked about sunglasses, right? That awful glare bouncing off a wet road or the surface of a lake. That's horizontally polarized light. Your sunglasses have vertical polarizers that just block it. Gone. And 3D movies? Same principle. They project two different images on the screen, each with a different polarization. The glasses you wear make sure your left eye only sees one image and your right eye sees the other, and your brain puts it together to create that 3D effect. It's also a huge deal in photography for cutting reflections, and even for engineers to see stress points in materials. It's everywhere.
So there you have it. A simple, everyday thing like tilting your sunglasses reveals this incredible, hidden structure to the light all around us. It really makes you wonder, doesn't it? What other amazing, invisible rules are governing our world, just hiding in plain sight, waiting for us to find the right way to look. Thanks for joining me for this one.